Hello there, and welcome to the Sleepy Science Channel. Find yourself a comfortable place to rest. Maybe you're already lying down, your body warm and heavy against the softness beneath you. Let your shoulders drop. Let your breath come slowly, without any effort at all. You don't need to do anything right now. You don't need to be anywhere. The only thing happening is this quiet moment and the gentle sound of words drifting toward you like leaves on still water. Tonight, we're going to talk about gravity, not in the way you might have heard about it in a bright, buzzing classroom, not with long equations or sharp diagrams. We're going to talk about it the way you talk about an old friend, something that has always been with you, something you've felt your whole life without ever needing a word for it. Gravity is the reason you're resting right now. It is the reason the blanket lies across you, the reason the pillow holds your head, the reason the whole quiet world is pressed softly against the earth tonight. And as we begin, just breathe. Let the air come in slowly. Let it go slowly. And let the story carry you. Imagine for a moment that you are floating in the middle of a very dark, very silent room. There is nothing pulling you in any direction. You are simply there, suspended, like a thought between two heartbeats. This is what the universe looked like, in a sense, before things came together, before stars, before planets, before the small blue world where you are resting right now. But the universe didn't stay empty. Matter appeared, tiny, tiny particles, each one so small you could never see it, each one carrying something remarkable inside it. They carried mass, and mass, it turns out, is not just a weight. It is not just how heavy something feels when you lift it. Mass is more like a presence, a quality of being. And every single thing that has mass does something extraordinary. It calls out to everything else that has mass too, softly, quietly, across any distance. This calling out is what we call gravity. It doesn't shout. It doesn't rush. It simply reaches, like the way warmth spreads from a fire or the way a scent drifts through a room. Gravity moves through space with a kind of unhurried certainty. It doesn't ask permission. It doesn't push. It only ever pulls, gently, steadily, without rest, without end. You are experiencing it right now. Your body, resting against whatever surface holds you, is being pulled toward the center of the earth. And the earth is being pulled, ever so slightly, toward you. Every object that has mass pulls every other object that has mass. A book on a shelf pulls the moon. The moon pulls you. It's not a force you can feel in those small scales, but it is real. And it is always happening, like a slow, invisible conversation between everything that exists. The word gravity comes from the Latin gravitas, which simply means heaviness, weight, seriousness. The Romans used it to describe the quality of a wise elder, someone whose presence settled a room. And in a way, that is exactly what gravity does. It settles things. It brings things together. It gives the universe its sense of order and repose. For most of human history, no one knew what gravity actually was. They felt it, of course. They watched apples fall and rivers flow downhill and stones sink in water. But why? That was the mystery. Some thought the earth had a kind of hunger for heavy things. Some thought that objects were drawn downward by their own nature, that heavy things simply belonged below, the way smoke belonged above. And then came a man who sat in a garden and watched an apple fall, or so the story goes, and began to wonder not just why the apple fell, but whether the very same pull that brought the apple to the ground might also be the pull that kept the moon in the sky. His name, of course, was Isaac Newton, and what he worked out changed everything. But we'll come back to him. For now, just rest in that thought, that the fall of an apple and the path of the moon might be the same thing, wearing different clothes. Let your eyes be soft now. Let the weight of your body sink a little deeper. You are held. You have always been held. The earth beneath you is holding you close, the way it holds every stone and every sea and every sleeping creature on its surface. There is something deeply peaceful about that if you let yourself feel it. You don't have to do anything to be held by gravity. You don't have to earn it or ask for it. It is simply there, like breath, like warmth, like the steady darkness of a quiet room at night. The force of gravity depends on two things, and they are both wonderfully simple. The first is mass, how much matter something contains. The more mass, the stronger the pull. The earth has an enormous amount of mass, which is why its gravitational pull is strong enough to keep you on the ground, to keep the oceans in their basins, to keep the atmosphere wrapped around the planet like a soft shell. A small stone has much less mass, and its pull is almost unimaginably faint. The second thing gravity depends on is distance. The farther apart two objects are, the weaker the pull between them. Double the distance, and the force becomes 4 times weaker. This is called an inverse square relationship, and it has a kind of elegant poetry to it. The further you drift from something, the more gently it holds you. But it never fully lets go. No matter how far apart two objects are, there is always some thread of gravity between them, thinner than a whisper, but unbroken. Think of that for a moment. You and a distant star, separated by unimaginable miles of cold, dark space, are still, technically, gravitationally connected. The pull is so faint, it could never be measured, never felt, never seen. But it exists. Everything in the universe is gently tugging on everything else, in one great, slow, silent conversation that has been going on since the very beginning of time. The first person to write this down in a way that could be measured and tested was Isaac Newton, and the equation he gave us is one of the most beautiful things in the history of human thought. Not because it is complicated, it isn't really, but because it is so clean, so spare, so perfectly fit to describe something as immense as the universe. He called it the law of universal gravitation, and that word, universal, meant everything, every object, every planet, every grain of sand and every blazing sun. One law covering all of it. Newton imagined gravity as a force, something that reaches across space from one object to another like an invisible hand pulling things together. In his picture of the world, space itself was just a backdrop, a flat stage on which things moved and fell and orbited. The force of gravity traveled across that stage instantaneously, connecting everything that had mass. This picture worked extraordinarily well for over 200 years. Newton's equations could predict the motions of the planets to remarkable accuracy. They could tell you where a cannonball would land, how fast a river would run, what path a comet would take through the inner solar system. The world made sense in a Newtonian way, orderly, mechanical, precise, like a great clock ticking quietly in the dark. And yet, there were tiny puzzles, small things that didn't quite fit. The orbit of Mercury, the innermost planet, wobbled ever so slightly in a way that Newton's equations couldn't fully explain. It was a small discrepancy, barely noticeable, easily set aside. But for people who paid attention to the very small and very precise, it nagged. And then, in the early years of the 20th century, a young man who had once dreamed of riding alongside a beam of light turned everything upside down. His name was Albert Einstein, and what he offered the world was not just a better equation, but an entirely new way of thinking about what space and time actually are. Close your eyes for a moment if you haven't already. Breathe. Imagine space not as an empty room, but as something more like a fabric, a vast, soft, invisible sheet that stretches in every direction, in all dimensions at once. It has a texture to it, a kind of give, a flexibility. And when something with mass settles into that fabric, it doesn't just sit there. It sinks into it. Gently, like a stone placed on a stretched silk cloth, it makes a curve, a dip, a slow, graceful hollow in the fabric of space. Einstein called this fabric spacetime. Not just space, but space and time woven together into one continuous thing. And what massive objects do to space-time, that bending, that curving, is what we experience as gravity. It isn't a force pulling us toward the Earth. It's the Earth bending the space around it, and we simply follow the curve, the way water follows the shape of a bowl it's poured into. This is a soft idea. Let it settle slowly. You don't need to grasp it all at once. Just rest with the image, the great fabric of space, gently dimpled by every massive thing within it. Stars like stones on silk, planets curving the space around them, and smaller things like moons, like spacecraft, like light itself, following the curves. Yes, even light follows the curves of space-time. Light, which travels faster than anything else in the universe, still bends when it passes near something massive. This was one of Einstein's most startling predictions, and in the year 1919, during a total solar eclipse, astronomers measured the positions of stars near the edge of the sun and found that their light had bent, had curved around the sun, exactly as Einstein predicted. The news traveled around the world. A new understanding had arrived. It's worth pausing on how strange and how beautiful this is. Before Einstein, people thought that space was just empty distance, a kind of nothing between things. But Einstein showed that space is something. It can bend, it can ripple, it can stretch and compress. It participates in the universe. It is not just the stage, it is part of the story. And you, right now, resting wherever you are sitting in curved space-time. The Earth's mass has bent the space and time around it, and you are resting at the bottom of that gentle curve, held there not by a hand or a hook, but by the shape of space itself. The very geometry of your surroundings is what keeps you close to the ground. If you've ever wondered why it always feels like the ground is down, it's because the ground is at the bottom of a curve in space-time, and everything in the universe tends to roll quietly and inevitably toward the bottom of curves. If you're enjoying these quiet journeys into the science of the natural world, you might like to leave a like on this video. It's a small thing, but it means a great deal, and it helps more people find their way here to rest. Let the image of that curve stay with you. Let your body feel it. Feel the gentle pull of the earth beneath you, and understand that you are not being pushed down or held down. You are simply following the natural shape of space. You are exactly where space-time invites you to be. There is a way to picture what Einstein was describing that is helpful and surprisingly soothing. Imagine a trampoline, that large circular sheet of stretched fabric, the kind you might find in a quiet backyard on a soft summer evening. Now imagine you place a heavy ball, like a bowling ball, right in the center. The fabric dips. It curves. There is a hollow, a slow bowl shape where the ball sits. Now, roll a marble across the trampoline. It doesn't travel in a straight line. It curves. If you roll it just right, it might circle the heavy ball for a while, going around and around, following the curve of the fabric. It doesn't need to be pushed or pulled by any force. It simply follows the shape of the surface it's traveling on. This is, more or less, what planets do around stars. The sun, with its enormous mass, curves space-time deeply around itself. And the planets, moving through that curved space-time, follow paths that curve around the sun. What we call an orbit is simply a path that follows the shape of space-time so perfectly that the moving object never arrives and never escapes. It just keeps following the curve endlessly, like a marble that found the perfect speed to circle the bowling ball. The Earth follows such a path around the sun, completing one full orbit every 365 days. The moon follows such a path around the Earth. Everything that orbits because of curved space-time, not because it is being pulled by a magical force, but because it is following the geometry of the universe. What is so restful about this idea is its quality of naturalness. There is nothing effortful about an orbit. There is no straining, no fighting, no working against anything. The moon isn't struggling to stay in the sky. It is simply doing the easiest thing, following the shape of the space it finds itself in. It is, in a sense, at rest. Moving, yes, but at rest within the logic of the universe. The way you are at rest right now, following the shape of the gravity well beneath you, settled comfortably at the bottom of the Earth's curve. Gravity is strongest close to a massive object and weakens as you move away. If you were standing on the surface of a very small, dense planet, gravity there might be weaker than it is on Earth. If you were standing on the surface of a very large, dense planet, you would feel much heavier, your own mass being pulled more strongly toward the planet's center. On the surface of Jupiter, you would weigh more than twice what you weigh on Earth. On the surface of Mars, you would weigh only a little more than a third of your Earth weight. Astronauts who travel to the International Space Station experience what we call microgravity. This is often described as weightlessness, but that isn't quite right. There is plenty of gravity up there. The space station is only about 400 kilometers above the Earth, and gravity at that distance is still about 90% as strong as it is on the ground. The reason astronauts float is not that there's no gravity, but that they are in free fall, constantly falling toward the Earth, but also moving sideways fast enough that they keep missing it. They are, like a marble on a trampoline, following a curve. And in that curve, there is a lovely floating piece. Imagine floating like that for a moment. No weight, no sense of up or down, just your body drifting slowly in warm silence. Every astronaut who has experienced this says there is something deeply calm about it. A feeling of freedom from the ordinary sense of heaviness, a return to something that feels almost like the beginning of things. The Earth's gravity is what holds our atmosphere in place. Without it, the air would simply drift away into space, molecule by molecule, carried off by the warmth of the sun. Gravity wraps the atmosphere around our planet like a soft blanket, holding it close, keeping the air warm and breathable, letting clouds form and rain fall and rivers run and oceans rest in their great blue basins. Every breath you take is a gift of gravity, and gravity is what makes rain fall. Water vapor rises into the atmosphere, carried up by warmth and wind, and forms clouds. Those clouds grow heavy with tiny water droplets, and when the droplets become large enough, gravity draws them down, gently but surely, back to the Earth. Rain is gravity made audible. The soft tap of drops on leaves and rooftops is the sound of space-time doing its quiet work. Feel the breath in your body now, moving slowly in and out. That breath is possible because of gravity. The air is here, staying close, because the Earth holds it. You are warm and held and safe because of this invisible, effortless force that has been at work since before the Earth existed. Long before the Earth existed, long before the sun began to burn, there was a cloud, not a cloud like the ones you might watch drift across a summer sky, not white and soft and lit by the afternoon. This was a cloud of gas and dust, vast and cold and dark, drifting slowly in the early universe. It had no particular shape. It had no center. It was just a spreading, thinning, barely there collection of hydrogen and helium, the two lightest elements, scattered across an immense region of space. And then, somewhere in that cloud, something happened. Perhaps a nearby star exploded, sending a shock wave rippling through the gas. Perhaps it was simply the slow accumulation of small fluctuations over millions of years. Whatever the cause, a small region of the cloud began to collapse inward. Gravity, responding to the very slight excess of mass in that region, began to pull the surrounding gas toward it, slowly at first, then faster still. As the gas fell inward, it began to spin, the way water spirals down a drain, pulled by the shape of the flow. The spinning cloud flattened into a disk, and at the center, the gas grew denser and hotter under the pressure of all the mass falling onto it from above. After perhaps 100,000 years of this slow gravitational collapse, the center became hot enough to ignite nuclear fusion. A star was born, our sun. The remaining disk of gas and dust around the young sun also began to clump, drawn together by gravity. Small particles bumped into each other and stuck together, growing into larger clumps, then pebbles, then boulders, then worlds. The whole process, from cloud to planets, took only a few tens of millions of years, which is a brief time by cosmic standards. Gravity did all of it. Gravity was the architect, the sculptor, the slow, patient force that turned a cloud of nothing in particular into a solar system. It is lovely to think about in these quiet moments before sleep. Everything you have ever seen, everything you have ever touched, every mountain and ocean and grain of sand on this planet, all of it was assembled by gravity. The iron in your blood was once scattered through a cloud of gas. The calcium in your bones was once part of the heart of a star. Gravity pulled it all together, not once, but over and over again across billions of years, into this particular arrangement of matter that is you resting here tonight. There is something deeply peaceful about being part of a process so old and so large. You are not separate from the universe. You are a piece of it, shaped by the same forces that shape stars and galaxies. Gravity doesn't treat you differently from the way it treats a mountain. It holds you just as it holds the seas. Let that thought settle in you like warmth. Let your breath slow. You are part of something enormous and ancient and gentle. The same quiet force that drew the first stars together is the force pressing you softly into your bed right now. Our moon was also made by gravity, though in a more dramatic way. About 4.5 billion years ago, a body roughly the size of Mars struck the young Earth in a tremendous collision. The impact threw enormous amounts of material into orbit, rock and vapor and liquid, and over time, gravity pulled all of that debris together into a sphere. That sphere became the moon. What is now a soft silver light in the night sky was once a cloud of hot rock circling the Earth, held in place by gravity, slowly condensing into the world we now see rising over quiet hills and resting on the surface of still water. The moon, in turn, has its own gentle gravitational effect on the Earth. Its pull tugs on the oceans, raising them slightly on the side of the Earth facing the moon. This is what causes the tides, the slow breathing of the sea, the twice daily rising and falling of the water along every coastline in the world. The tide is the moon's touch, reaching across nearly 400,000 kilometers of space to move the water on our planet. Gravity, even at that distance, is still speaking. If you are near the ocean in your thoughts tonight, you might imagine that movement, the water drawing in, resting for a moment at the edge of its fullness, then easing slowly back and forth, back and forth, the ocean breathing under the pull of a distant world. There is something extraordinarily soothing about the tides. They have been happening for 4 billion years. They will go on happening long after any of us are here to watch them. Do check out the playlist on this channel. There are many other quiet stories about the natural world waiting there for you, each one made to help you rest and carry you gently into sleep. Gravity is patient in a way that nothing else quite is. It works not just over distances, but over time, in scales that are almost impossible to imagine. Consider what happens to a star when it runs out of fuel. For millions or billions of years, a star burns, producing energy through nuclear fusion, and that energy pushes outward, counteracting the inward pull of gravity. There is a balance, a careful, ongoing negotiation between the outward pressure of heat and light and the inward pressure of gravity. As long as the fuel lasts, the star holds its shape. But when the fuel runs out, the outward pressure stops, and then gravity wins. The star collapses inward rapidly under its own weight. What happens next depends on how massive the star was. A star like our sun will collapse into a small, dense, glowing object called a white dwarf, roughly the size of the Earth, but containing as much mass as the sun. A more massive star might collapse into something even smaller and denser, a neutron star in which all the matter is packed together so tightly that a single teaspoon of its material would weigh about 1 billion tons on Earth. And the most massive stars of all collapse further still into something so dense that not even light can escape from them. This is a black hole. The gravity at the surface of a black hole is so strong that space-time curves back on itself completely, forming a kind of closed loop. Anything that crosses the boundary, called the event horizon, cannot get back out. Not a rock, not a signal, not a photon of light. Black holes might sound frightening, but they are actually quite peaceful in the vast majority of space. They don't roam around the universe, gobbling things up. They sit quietly wherever they formed, curving the space around them and affecting only things that come very close. From a safe distance, a black hole is gravitationally similar to a star of the same mass. If our sun were somehow replaced by a black hole of equal mass, the planets would continue orbiting exactly as they do now. The darkness would increase, certainly, and the warmth would vanish, but the orbits themselves would be unchanged. Gravity doesn't care what form the mass takes. There is something almost contemplative about a black hole when you think about it this way. A point of perfect stillness around which the rest of the universe quietly orbits. A place where time itself slows down, because near a very strong gravitational field, time runs differently. If you could hover very close to a black hole without falling in, you would age more slowly than someone far away. Time, in Einstein's universe, is not fixed and unchanging. It bends with space. It is woven into the fabric too. The idea that time can slow down near gravity seems strange, but it is real, and it is measurable. The GPS satellites that orbit the Earth experience weaker gravity than we do on the ground, and as a result, their clocks run slightly faster. When engineers designed GPS, they had to account for this. The difference is tiny, only about 38 microseconds per day. But if you didn't correct for it, the navigation system would drift off by many kilometers. Einstein's theory of curved space-time is built into the technology in your pocket. Lie there now and feel the slight heaviness of your body, the comfortable weight of rest. Time is moving at a very slightly different speed for you than it would for someone floating in space, far from any planet. You are deep in the Earth's gravity well, and your clocks tick just slightly slower than they would in the empty void between stars. It is an imperceptibly small difference, but it is real. You are living in curved space-time tonight, just as you always have been, and time is moving through you at the exact rate that your place in the universe allows. There is a word in German, Weltschmerz, which means a kind of ache for the world, a tenderness about existence. And I think there is something like that in the relationship between gravity and time. The universe is not a hard, fixed thing. It is soft in ways you might not expect. Space bends, time bends. The very fabric of existence responds to the presence of matter, and what we experience as weight, as groundedness, as the feeling of being held, all of that is the universe responding to us. We are not separate from the laws of physics. We are inside them, woven into them, shaped by them, and shaping them in return, however slightly. Your body, pressed against the earth tonight, is a small but real curve in the fabric of space-time. A small gravity well, pulling everything nearby, the air around you, the objects on the table, the dust floating in the dark room, ever so faintly toward you. You are not just subject to gravity, you are a source of it. One of the most extraordinary things about gravity is that it is, in a sense, the weakest of the fundamental forces. There are 4 forces that govern the interactions of everything in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Of these 4, gravity is by far the faintest when you compare it at the scale of individual particles. Consider this. A small refrigerator magnet can hold a paperclip against the Earth's entire gravitational pull. The electromagnetic force in that little magnet overcomes the gravity of an entire planet. At the scale of atoms and particles, gravity is almost irrelevant. So weak that physicists often ignore it entirely when calculating how particles interact. And yet, at the scale of planets and stars and galaxies, gravity is the dominant force. Why? because gravity has two properties that make it extraordinary over large scales. First, it has infinite range. It never fully turns off, no matter how far apart two objects are. Second, it is always attractive, unlike electromagnetism, which can attract or repel depending on the charges involved. Gravity only ever pulls. It never pushes. And because it only pulls, all the gravity from all the matter in a large object, every atom, every particle, adds up in the same direction. Mass accumulates gravity. So while gravity is faint between two individual particles, when you pile up enough mass, as much as a planet or a star or a galaxy, the gravity becomes immense. The Earth has roughly 6 times 10 to the 24th kilograms of mass, and all of that gravity is pointing inward toward the center. The sum of those tiny, weak gravitational pulls from every atom in the planet is enough to hold you firmly to the ground, to keep the atmosphere from drifting away, to hold the moon in place 400,000 kilometers above. It is like the difference between a single whisper and a chorus. One voice whispering is almost nothing, but when every person in a great hall whispers at once, pointing in the same direction, the sound becomes a presence. Gravity is the cosmic chorus of mass, always whispering inward, never quite silent. Physicists have wondered for a long time whether gravity might have a carrier particle, the way electromagnetic force is carried by photons. This hypothetical particle is called the graviton. No one has ever detected one. They would be almost impossibly difficult to observe. But theoretically, if gravity can be described in the same language as the other forces, it should be carried by something. For now, the graviton remains a beautiful idea, a ghost in the equations, waiting to be found or explained away. There is also a mystery at the heart of gravity that remains open. Einstein's general relativity describes gravity beautifully at large scales: planets, stars, galaxies. Quantum mechanics describes the other forces beautifully at tiny scales: atoms, particles, energy. But these two frameworks, each extraordinarily successful in its own domain, don't fit together cleanly. When you try to apply quantum mechanics to gravity, the equations produce nonsense. Infinities appear where they shouldn't. The two greatest theories in physics are, in a deep sense, not yet fully compatible. This is one of the great open questions in all of science. Physicists call the hoped-for solution a theory of quantum gravity, and some of the most brilliant minds in the world have spent their careers searching for it. String theory is one attempt. Loop quantum gravity is another. Neither is yet confirmed. The answer, when it comes, may reshape our understanding of space and time and matter as profoundly as Einstein reshaped it over a century ago. But here is the peaceful thought to carry with you. The fact that we don't yet fully understand gravity doesn't mean it is uncertain. Gravity works. It has always worked. Long before Newton gave it a name, long before Einstein described it as curved spacetime, gravity was holding the seas in place and keeping the moon in the sky and pulling the rain softly back to the ground. The mystery at its edges doesn't diminish the quiet, certain fact of it. you are held. Without knowing any equation, without understanding any theory, your body knows this. It knows the ground, knows the weight of rest, knows the gentle, reliable pull that has kept it safe and settled every moment of its life. That knowledge is not in the mind. It is in the bones. If this story is helping you find your way towards sleep, a small like or a kind comment would mean a great deal. It takes only a moment, and it lets others find their way here too. Gravity shapes not just individual objects, but the largest structures in the universe. Look at the night sky on a clear evening, away from the lights of towns and roads, and you see stars scattered across the dark. But those stars are not scattered randomly. They are gathered together in vast groups called galaxies, each containing hundreds of billions of stars, all held together by their mutual gravity, all rotating slowly around a common center. Our galaxy is called the Milky Way. It is a spiral galaxy, a great flat disk with arms of stars curling outward from a central bulge, like the slow spin of a pinwheel. If you could rise above it and look down, it would look something like a soft, glowing, faintly barred spiral, turning very, very slowly in the dark. One full rotation of the Milky Way takes about 230 million years. The Sun has completed this journey roughly 20 times since the Earth was formed. At the center of the Milky Way, and at the center of most large galaxies, there is a supermassive black hole. Ours is called Sagittarius A star, and it is about 4 million times the mass of the Sun. It lies about 26,000 light years from Earth, far in the direction of the constellation Sagittarius, behind great clouds of gas and dust. It sits there, quietly, holding the inner galaxy together with its immense gravity. Galaxies themselves are drawn together by gravity into groups and clusters. Our Milky Way belongs to a small group called the Local Group, which includes about 50 galaxies. Among them, our nearest large neighbor, the Andromeda Galaxy. Andromeda is visible from Earth on dark nights as a faint smear of light, the most distant thing human eyes can see without a telescope. It is about 2.5 million light years away, and it is moving toward us, drawn by gravity. In about 4 to 5 billion years, the Milky Way and Andromeda will merge, not in a violent collision of stars, but in a slow gravitational dance, the two galaxies passing through each other and gradually combining into one larger elliptical galaxy. Even at this enormous scale, two entire galaxies, billions of stars each, the merger will be slow and gentle. Because stars are so far apart, even within a galaxy, the chance of any two actually colliding is very small. They will pass through each other like two clouds of fireflies drifting together on a summer night. Their individual lights never quite touching, their swarms slowly mingling into one, and clusters of galaxies are drawn together into superclusters, and superclusters are arranged along vast filaments of dark matter like dewdrops on an enormous web surrounding great empty voids. The largest structures in the universe, the cosmic web, are shaped entirely by gravity, the echoes of tiny fluctuations in the very early universe, amplified over billions of years into the intricate architecture of everything that exists. Lie there and imagine it, not anxiously, but softly, the vastness of it. A universe of webs and voids, of spinning galaxies and slow dances between clusters, of ancient gravity working patiently across billions of light years. And at the end of one small arm of one ordinary spiral galaxy, a single yellow star, and around it a small blue planet. And on that planet, on a quiet night, you, resting, breathing, held. The universe does not feel distant from you if you let it be close. The gravity holding you to the earth is the same force shaping galaxies. The atoms in your body were forged in the hearts of stars and scattered through space and pulled together by gravity into everything you are. You are not separate from all of that. You are made of it. You're a small, warm, temporary arrangement of the universe resting at the bottom of a gentle curve in spacetime. And it is enough. It is more than enough. Dark matter is another great mystery woven into the story of gravity. When astronomers study the rotation of galaxies, they find that the outer regions spin faster than they should, faster than can be explained by the visible mass of stars and gas alone. Something else must be there, something with mass, something that exerts gravitational pull, but doesn't emit or absorb light. This something is called dark matter, and it is thought to make up about 27% of the total mass energy of the universe. We cannot see it. We cannot touch it. We know it only by its gravity. Dark matter is like a scaffolding hidden behind a tapestry. You see the tapestry, the stars and galaxies, but what holds it up, what gives it its shape, is something you cannot directly observe. The web-like structure of the cosmos, the way galaxies cluster and cluster around their walls, all of that is shaped by dark matter's gravity, the invisible hand that drew the first structures out of the early universe's fog. Rest now in that mystery too. Not every question needs an answer to be beautiful. The dark matter is there, holding the shape of the cosmos, whether we understand it fully or not. And the night sky above you, if you were to step outside, would be lit by stars held in place by forces we are still working to understand. The universe is patient with our questions. It has time. There is a phenomenon called gravitational lensing that is among the most visually beautiful things in all of astronomy. When light from a very distant galaxy travels toward us, it may pass close to a massive object, a galaxy cluster, between us and the distant source. The massive object curves space-time, and the light, following those curves, bends around it. The result, as seen from Earth, is that the distant galaxy appears distorted, stretched into arcs, or multiplied into rings, or smeared into ghost-like copies of itself surrounding the closer object. These rings of distorted light are called Einstein rings, named for the man who predicted they should exist. When astronomers photograph a distant region of sky and see one, there is always something moving about it, a vision of something so far away that its light has traveled for billions of years, bent around an entire galaxy cluster on the way, arriving at our eyes as a beautiful arc of blue or white against the dark. Light itself, curved by gravity. The universe using the mass of whole galaxy clusters as a lens. Gravitational lensing isn't just beautiful, it's also useful. Because the degree of bending depends on the mass of the lensing object, astronomers can measure the total mass of galaxy clusters this way, including the dark matter component that can't be seen directly. The universe, in effect, provides its own instruments. There is also gravitational time dilation, the slowing of time in the presence of strong gravity, which we touched on earlier. But the everyday version of this is worth dwelling on again. Every moment of your life, time has been passing at a very slightly different rate, depending on where you are. When you are at high altitude, on a mountain, in an airplane, you are farther from the center of the Earth, in slightly weaker gravity, and your clock runs very slightly faster. When you are at sea level, deeper in the Earth's gravity well, your clock runs very slightly slower. The difference is extraordinarily small. We're talking about fractions of a microsecond over a lifetime. But the fact that it is real is remarkable. Time is not a steady river flowing at the same speed everywhere. It is more like a stream that runs faster and slower depending on the terrain. And the terrain here is gravity. Imagine the life of a deep-sea creature living at the bottom of the ocean, kilometers below the surface, deeper in the Earth's gravity well than any human has ever rested for long. Its time ticks just a touch more slowly than ours. Over a long enough lifetime, its clocks would fall fractionally behind ours. Of course, it has no clocks. It has no concept of time dilation. It simply lives in the quiet, dark pressure of the deep, unaware that the universe is treating its moments with the softest, most imperceptible difference from ours. We are all of us moving through time at speeds shaped by our place in the universe's gravitational landscape. Yours tonight is shaped by the earth beneath you, by the slight altitude of wherever you are, by your distance from the center of this particular gravity well. Your time is yours, moving at your rate, shaped by your position in the cosmos. Gravity also plays a role in the birth of new stars happening right now, tonight, in distant clouds of gas and dust. The Orion Nebula, visible to the naked eye on winter evenings as a faint haze below Orion's belt, is an active star-forming region where dozens of new stars have formed in the last 1,000,000 years. Deep inside those swirling clouds of gas, gravity is pulling matter together, just as it pulled our sun together billions of years ago. Stars are being born tonight. Gravity is building new suns in the dark, and in those young stellar systems, the same gravitational process that formed our Earth is likely underway. Gas and dust in the disk around the new star, clumping together, pebble by pebble, grain by grain, pulled together into planets. Worlds are forming right now, somewhere in the dark, built grain by grain and moment by moment by the patient work of gravity. Some of those worlds may have oceans, some may have rain. Some may, in a very long time, be places where something pauses on a quiet evening and looks up at a night sky and wonders about the force that holds it to the ground. The playlist on this channel has other stories like this one, about oceans and forests and stars and the small, patient lives of insects, if you'd like company on another night of rest. Gravity waves, not water waves, not sound waves, but waves in the fabric of space-time itself. Einstein predicted these in 1916, and for 100 years they were theoretical, elegant, necessary, but undetected. The problem is that gravitational waves are extraordinarily faint. Even the most powerful events in the universe produce ripples in space-time that, by the time they reach Earth, are smaller than 1,000th the width of a proton. Detecting them seemed nearly impossible. But humans are persistent and curious and willing to build very patient, very sensitive instruments. In the late 20th and early 21st centuries, scientists built two enormous detectors in the United States called LIGO, the Laser Interferometer Gravitational Wave Observatory. Each detector is an L-shaped tunnel, 4 kilometers on each arm, built to measure the tiniest possible changes in the length of those arms. If a gravitational wave passes through, it stretches space-time in one direction and compresses it in another. And the tunnels change length by an amount so small it is almost beyond imagining. In September 2015, LIGO detected something, a signal lasting about 1/5 of a second, a brief chirp in the data. When the scientists analyzed it, they found it matched what was expected from 2 black holes, each about 30 times the mass of the Sun, spiraling toward each other across 1 billion light-years of space, and finally merging. In the final fraction of a second before they merged, they were losing energy so fast that the power being radiated was greater than the combined luminosity of all the stars in the observable universe. And what was being radiated was not light. It was gravity, ripples in space-time spreading outward from the collision at the speed of light. Those ripples traveled for over 1 billion years. They passed through galaxies, through the spaces between galaxies, through our own galaxy, through the solar system. And on a September morning in 2015, they arrived at Earth and passed through the detectors at LIGO, stretching and squeezing space-time by a distance 4,000 times smaller than the width of a proton. And the machines were sensitive enough to notice. It is one of the most moving things in the whole history of science. 2 black holes merging 1 billion years ago, 1 billion light-years away. The event was so violent that space itself rang like a bell. And 1 billion years later, on a quiet morning in Louisiana and in Washington State, that ringing arrived, and we heard it. Let that sit with you for a moment. The universe has been sending us messages for billions of years, written in the language of space-time itself, and we have only just begun to learn to read them. What else is out there, speaking in the quiet grammar of gravitational waves, waiting for us to build the instruments to listen. The detection of gravitational waves opened a new window on the universe, the way the telescope opened a new window 400 years ago. Before telescopes, we knew only what our eyes could see. With telescopes, we discovered planets and nebulae and galaxies. With gravitational wave detectors, we are beginning to hear events that are completely invisible to light. Black hole mergers, neutron-star collisions, perhaps even echoes of the very beginning of the universe. In 2017, LIGO detected the merger of two neutron stars, objects so dense that a sugar cube-sized piece of neutron star material would weigh about 1 billion tons. The gravitational wave from that merger was accompanied by a burst of gamma rays detected by satellites, and then by light from the afterglow detected by telescopes around the world. For the first time, an event in space was observed simultaneously in gravitational waves and in light. A new era had begun. You, resting there, are part of the species that built those instruments. That patient, curious, gentle effort, the decades of design and testing and careful measurement, that is what humans do at their best. They listen, they wonder, they build beautiful machines to hear the universe whisper. Even the way you move through the air is a story of gravity. Every time you take a step, you push down against the ground, and the ground pushes back up against you just enough to move you forward, and gravity pulls you back down, and your next foot falls, and you move through the world in this constant falling and catching rhythm. Walking is, in a sense, a controlled fall. You lean forward, gravity begins to pull you down, and your leg swings out to catch you, over and over in every step you have ever taken. Runners know this feeling. At faster speeds, the moments of flight grow longer. There are fractions of a second in a sprint where both feet are off the ground, where you are truly, briefly, airborne. You are following a tiny arc through the air, a tiny parabola, a brief flight across curved space-time before gravity brings you back to the surface. Even running is a dance with gravity. Birds, of course, have mastered this dance. A bird in flight is constantly using the air and its wings to counteract gravity, to stay aloft. But it is also using gravity. It glides, it descends, it uses the pull of the earth as part of its rhythm. A soaring hawk riding a thermal is not fighting gravity. It is using the warm air rising from the ground, itself a product of the sun's uneven warming, to climb. And then it glides, following gravity's curve, at a speed and angle that lets it travel far with minimal effort. Nature found the path of least resistance long ago. Seeds have their own relationship with gravity. A maple seed, that tiny winged thing shaped like a little propeller, falls from the tree in autumn and spins as it falls, the rotation slowing its descent, carrying it sideways on the breeze. Gravity pulls it down. The air beneath its wing holds it up for a moment, and the combination of the two carries it away from the parent tree, off to find its own patch of soil. Gravity is part of the maple's plan for its children. Dandelion seeds drift on their white parachutes, each one so light that the slightest air current can carry it far before gravity finally brings it gently to rest. The dandelion has evolved to use gravity's inevitability to take the time available before a seed must land and turn it into a journey. There is something very beautiful about this. A plant that uses the pull of the earth the way a sailor uses the wind to go somewhere new. Acorns fall straight down, heavy, solid. They land close to the parent tree, often rolling a little way before they rest. Their size and density mean that gravity brings them to earth quickly, but squirrels gather them and carry them away, burying them for later, and forgetting many, so that new oaks grow far from where they fell. Even the straightforward fall of an acorn is part of a longer journey. Water, of course, is shaped entirely by gravity. Rain falls. Rivers flow downhill. Glaciers creep slowly down mountainsides. Oceans rest in the lowest parts of the world. Every water cycle, every cloud and rain and river and sea is gravity at work, pulling water through its endless journey from cloud to ground to sea to cloud again. The sound of rain on a roof at night is gravity at work. The murmur of a stream is gravity at work. The deep, slow swell of the open ocean is gravity at work. Lie there and listen, if you can, to any soft sound near you. Perhaps rain, perhaps wind, perhaps only the quiet of a still house and the very faint, almost imagined sound of the world outside. All of it, whatever movement is out there, whatever falling and flowing and settling, is gravity, the background hum of the universe, doing what it has always done. Water droplets in a cloud are suspended by the updraft of warm air, held up briefly against gravity. When they grow large enough, heavy enough, when the sum of all that water finally outweighs the air's ability to hold it, they fall. A raindrop is the moment when gravity wins the argument with the sky, and when it lands on a leaf, on a window, on the surface of a still pond, it makes a small perfect circle, spreading outward in all directions, gravity sending it flat against the surface of the water, the ripple fading slowly into stillness. That stillness after the ripple fades, that is where you are heading tonight. Mountains exist because of gravity, and in spite of it. When tectonic plates collide, the immense forces in the Earth's crust push rock upward. But gravity is always working against this, always pulling the mountain back down, always causing rocks to crack and crumble and slide toward lower elevations. A mountain is the result of the ongoing negotiation between the forces pushing it up and the gravity pulling it down. The Himalayas, the highest mountain range on Earth, are still growing. The Indian subcontinent continues to push northward into Eurasia, and the rock crumples and rises. But every year, erosion, driven partly by gravity, partly by water and ice, carries particles of rock downhill into rivers toward the sea. In the very long run, every mountain is falling. Gravity wins. Mountains are temporary gestures, but on the time scale of a human life, mountains are as permanent and solid as anything can be. They have a quality of gravity about them, that older meaning, that sense of deep, unhurried presence. A mountain doesn't rush. It just is there, enormous and quiet, shaped partly by the same force that holds you to the ground tonight. The valleys between mountains are also gifts of gravity, places where rock has been worn away and water has collected, where soil has gathered and forests have grown, where rivers run in the shade of trees. The shape of every valley on earth is a record of the patient work of water and gravity over millions of years. Caves are spaces in rock where water has slowly dissolved the stone, often flowing downward, following gravity, leaving hollow passages behind. Stalactites hang from cave ceilings because mineral-rich water drips down and deposits its minerals as it falls. Stalagmites rise from cave floors where the same drops land. Both structures are built by falling, by water following gravity, drip by drip over thousands of years, building these silent stone formations in the dark. Imagine the inside of a large cave at night, the complete silence, the absence of light, the slow drip of water somewhere in the dark, each drop following its small parabolic path from ceiling to floor. Thousands of years of dripping. Stalactites that have grown for 10,000 years from water following gravity. There is a patience in those formations that is almost impossible to comprehend, a slowness that makes even the mountains seem hasty. Soil itself settles by gravity. When rain moves through soil, it carries particles downward. Over thousands of years, the finest particles settle deepest and layers form. The stratigraphy that geologists read like the pages of a very slow book. Every layer is a chapter written partly by gravity. The depth of a layer tells you something about the time that passed as gravity and rain did their sorting. The earth keeps its own records written downward. Even the shape of a river delta, those spreading intricate patterns where a river meets the sea, is shaped by gravity. The river flows downhill to the sea, carrying sediment. Where the water slows and spreads, the heavier sediment drops first, the lighter particles carried further. Over centuries, these deposits build up into a delta, a spreading fan of new land-grown grain by grain from the pull of the earth. The Nile Delta, the Mississippi Delta, the Ganges Delta, some of the most fertile places on earth, built by rivers depositing sediment, driven by gravity over millions of years. Some of the oldest human civilizations settled in these deltas, drawn to the richness of the soil, to the water, to the gentleness of the flat land, where gravity had done such patient work. Rest there for a moment in the thought of those flat, fertile, water-rich places. Fields in the early morning, mist lying close to the ground, rivers moving slowly to the sea, birds beginning to stir, the soft light of dawn coming in low across the water. Everything settled, everything at its lowest point, everything held in place by the gentle insistence of gravity. You are at your lowest point right now, too. Lying down, your body spread across its largest possible surface, offering as much of yourself as possible to the ground. This is what gravity asks of you, and this is what sleep asks of you, to let go, to settle, to stop pushing up against it. The gravitational pull of the sun is responsible for much more than just keeping the planets in orbit. It shapes the weather on Earth in roundabout ways. The sun heats the earth unevenly, more at the equator, less at the poles. And this uneven heating causes temperature differences, which cause air pressure differences, which cause wind. Winds move water vapor, which forms clouds, which causes rain. All of this is at root driven by the sun's warmth reaching us across 93 million miles. And the sun's warmth reaches us at this distance because of gravity. Gravity held the solar system in its shape, kept the planets at their particular distances, kept the Earth at the precise distance where water can exist in all three states, where life can breathe and grow. The gravitational pull of the sun even has a slight effect on the shape of the Earth. The Earth is not a perfect sphere. It bulges slightly at the equator because the spinning Earth throws material outward, and that material is in a constant equilibrium between gravity pulling inward and the centrifugal effect pushing outward. The equatorial bulge is about 21 kilometers. So, the Earth's radius at the equator is slightly larger than at the poles. If you are standing on the equator, you are very slightly farther from the center of the Earth than if you were standing at the poles. And gravity there is very slightly weaker. This means that you weigh very slightly less at the equator than at the poles. The difference is small, about 0.5%, but it is real. If you could feel it, it would be like putting down a very light backpack, a kind of lightening, a small release of weight, just from where you stand on the spinning Earth. The moon's gravity, which we mentioned in relation to tides, also slows the Earth's rotation very gradually. Every century, the day grows a tiny bit longer, by about 2 milliseconds per 100 years. 4 billion years ago, a day on Earth was only about 6 hours long. The Earth was spinning much faster, and the moon was much closer, its tidal forces stronger. Over billions of years, the moon's gravitational tugging has slowed the Earth's spin, and the days have grown longer, and the moon has moved gradually farther away. This process will continue for billions of years to come. In the very far future, many billions of years from now, the Earth and moon will reach a state called tidal locking, where the same side of the Earth always faces the moon, as the same side of the moon already always faces the Earth. A day on Earth would then be as long as a month. The tides would be still. The sun would rise and set only once per lunar cycle. Everything would be slower, more patient, more settled. There is something almost comfortable about imagining that future Earth, the deep, slow rhythms of it, the long days and long nights, the unhurried movement of the sun across the sky, although humans would never be there to see it. Long before then, the sun itself will have changed, but the slow, patient physics will still be happening. Gravity will still be at work. The universe doesn't rush. The connection between gravity and the moon's phases is another gentle rhythm you can carry with you. The moon orbits the Earth once every 29.5 days, and as it does, the angle between the sun, the moon, and the Earth changes, giving us the phases. New moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, waning crescent, and back to new. These phases have been marking time for as long as there have been eyes to observe them. The tides follow the moon, and the moon follows its orbit, and the orbit follows the curve of space-time, and it all goes back to gravity. Wherever you are right now, the moon is somewhere in the sky, above the horizon or below it, lit by the sun to some particular degree of fullness, moving slowly along its path. It has been following that path for 4 billion years. It will continue following it for billions more. Its presence is one of the most reliable things in the universe, not constant in its phase, but constant in its motion, constant in its company to the earth. Feel the quiet assurance of that. The moon is in the sky. Gravity is holding everything in place. The world is moving through the night, slowly, steadily, on its ancient path. There is a version of gravity that you can feel most directly on a swing. Remember swinging as a child, the way the arc carried you forward and up, your weight feeling lighter at the top, heavier at the bottom, the whole motion so smooth and predictable it felt almost like breathing. What you were doing on that swing was tracing a pendulum path, a curved arc in space-time, your body trading between potential energy, height, and kinetic energy, speed, in a perfect, continuous exchange. Gravity was the engine. The swing was just the structure that let you feel it clearly. Pendulums have been used to keep time for centuries, because the period of a pendulum, the time it takes to swing from one side to the other and back, depends only on its length, not on how hard you push it or how heavy the weight is. A pendulum of a given length always takes the same time to swing, as long as it's swinging with small arcs. This regularity was enormously valuable before electronic clocks. A swinging pendulum was a piece of gravity turned into a timekeeper. The old grandfather clocks, standing tall in quiet hallways, their pendulums swinging back and forth in the dim light. Those clocks were measuring time by gravity. Every tick was one swing of a pendulum, gravity pulling it one way, inertia carrying it the other. Tick, tock. The sound of gravity keeping time. The word pendulum comes from the Latin pendulus, meaning hanging. And there is something about a hanging, swinging thing that is fundamentally soothing. The metronome quality of it, the predictability, the gentle arc. A hammock swings slightly in a breeze. A lantern sways on a ship. A child on a swing pumps their legs and rises and falls. All of these are pendulum motions, all of them following the mathematics that gravity draws in the air. Galileo, who lived in the late 1500s and early 1600s, is said to have noticed the regular swing of a chandelier in a cathedral, timing it against his own pulse, and realized that it kept perfect time, regardless of how wide its arc was. This observation eventually led to the development of the pendulum clock, which was far more accurate than any timekeeper that had come before it. Gravity, again, providing a clock. The universe always had time. It just took humans a while to learn to read it. using the tools gravity provided. There is another kind of motion that gravity produces, less well known, but equally beautiful. The Lissa-Juice figures traced by two pendulums swinging at right angles to each other. If you attach a pen to the bottom of a pendulum and let it swing over paper, it traces a straight line. But if you swing two pendulums at right angles and couple them, the pen traces a figure eight, or a flowing curve, or a beautiful, intricate loop depending on the relative periods. These shapes, called Lissa-Juice figures, are entirely the product of gravity and geometry. No design, no intention, just the mathematics of pendulums expressing themselves on paper. The ocean has its own kind of pendulum motion. Seiches are standing waves that occur in enclosed or semi-enclosed bodies of water, lakes, bays, harbors. If wind or pressure changes disturb the water, it can slosh back and forth in a regular oscillation, like water in a bowl being tilted. The water rises at one end and falls at the other, then reverses again. This can go on for hours after the initial disturbance. The water in a lake quietly sloshing back and forth, driven by gravity, the oscillation slowly dying as energy is lost to friction. Lake Geneva, the large lake on the border of Switzerland and France, experiences seiches regularly. After a strong wind, the lake level can differ by a meter or more between its two ends, the water slowly swinging back and forth. If you were sitting on the shore at night, watching the water, you might not even notice it happening. The movement is so slow, just the lake breathing, gravity pulling the water first one way, then the other, in its own long, slow pendulum swing. The feeling of being on a very large, very slow pendulum, or perhaps being rocked very slowly by water, is one of the deepest kinds of rest. Boats on still water, hammocks in a gentle breeze, the slow swinging rhythm that gravity provides, steady and certain and without end. Let your breath become that rhythm now, in and out, slow and easy. Gravity doing its quiet work, your body settling deeper with every breath. Gravity has shaped the architecture of living things in ways we rarely notice. Your own body is a product of gravity, standing upright, with your spine aligned vertically. Your skeleton is engineered to transfer the weight of your body through your hips, your legs, your feet, and down into the ground. Your spine is not a straight column, but a gentle S-curve, which allows it to absorb the shocks of walking and running while remaining strong under vertical load. The curve of your spine is, in part, an answer to gravity. The bones of your foot are arranged in a complex arch, the plantar arch, which distributes the force of your weight across the whole foot, preventing any single point from bearing all the load. Gravity is the force this arch is designed to handle. It evolved over millions of years of human ancestors walking upright, each generation refining the structure a little more, until you have this remarkably efficient arrangement of bones and ligaments that can carry you through a lifetime of steps. Trees deal with gravity in their own architectural ways. A tree trunk is not solid all the way through. It has a core of dense heartwood surrounded by living sapwood, and this arrangement gives it both strength and flexibility. A truly rigid tree would snap in a storm. A truly flexible tree would bend to the ground. The architecture of wood is a balance, strong enough to stand under the weight of thousands of kilograms of branches, leaves, and sometimes snow, flexible enough to sway in the wind without breaking. The roots of a tree deal with gravity too, but in reverse. They anchor the tree into the ground against the forces that might pull it sideways or even upward in a strong wind. Deep tap roots and wide-spreading surface roots work together to hold the tree in place. A fallen tree, with its root ball exposed, shows you how complex and extensive this anchor system is. A tangled mass of roots, often as wide as the tree is tall, all of it designed to resist the lateral forces that weather applies to a structure primarily shaped by gravity. The great sequoias of California, the tallest living things on Earth, reach heights of over 100 meters. The forces on such a structure are enormous. The weight of the crown, the leverage of wind on such a tall trunk, the sheer quantity of water and nutrients that must be pulled upward from the roots to the topmost leaves. How does water get to the top of a 100-meter tree? Not by a pump, by a combination of capillary action and transpiration. Water evaporating from the leaves creates a kind of suction that pulls water up through the tree's vascular system against gravity from root to crown. The tree is, in a sense, drinking constantly, pulling water upward against the pull that wants to bring everything down. There is a quiet determination in that image. The ancient tree standing in a forest, pulling water upward against gravity, moment by moment, year after year, century after century. Some of the oldest sequoias are 3,000 years old. For 3,000 years, they have been standing against gravity, pulling their water up, bearing their enormous weight with quiet, distributed strength. You, too, spend your waking hours working against gravity in small ways, sitting upright, standing, walking, lifting. Sleep is the time when you lay that work down. When you lie flat, your spine decompresses, your muscles relax, your whole body distributes its weight across the widest possible surface, and gravity no longer requires any effort from you. You can just be held. Astronauts returning from long missions in microgravity find that their spines have lengthened by an inch or two. The vertebrae, without gravity compressing them, spread slightly apart. Back on Earth over weeks, the spine returns to its normal length as gravity reasserts its gentle pressure. Your spine is not a fixed thing. It is in constant dialogue with gravity, compressed and lengthened by it throughout every day. And as you lie down now, you're having that same conversation. Let the compression ease. Let the vertebrae find their resting distance. Let the whole architecture of your body, built over millions of years of evolution to stand upright, to walk, to carry, put down its work for tonight. You don't need to stand right now. You don't need to move. Gravity will hold you here gently, quietly, all through the night. We have traveled a long way tonight, from the quiet weight of your body resting on the ground all the way out to the edge of the observable universe, from the pendulum of a grandfather clock to the merger of two black holes, from the fall of a raindrop to the slow rotation of the Milky Way. And all of it, has been gravity, the same quiet pull working at every scale in every place since the very beginning of time. Einstein's great insight was that gravity is not really a force at all. It is geometry. It is the shape of space-time in the presence of mass. And that means that you, resting there, are not being pushed down or pulled down. You are resting in a curve. The earth beneath you has bent the space and time around it, and you are lying at the bottom of that curve, as naturally and easily as a bead resting in the bottom of a bowl. There is no effort required. There is no tension. You are in exactly the place that the geometry of the universe has prepared for you. Let that thought be the last one you hold tonight. Not a complicated thought, not a thought that requires anything of you. Just this: you are resting in a curve in space-time. The universe itself has shaped a place for you. Not just for you, of course, but for everything on this small planet. And you are there, in it, held without effort, without needing to ask. The stars overhead are following their own curves. The moon is following its long, gentle arc. The earth is following its path around the sun. The sun is following its slow orbit around the Milky Way. Everything is in motion. Everything is following the curves that mass has carved into space-time, and everything is, in the deepest sense, exactly where physics says it should be. You are part of that. Your atoms are part of the universe, following the laws of physics, resting in the configuration that billions of years of gravity and chemistry have assembled. You are made of stardust. You are held by curved space-time. You are breathing air that gravity has kept close to this planet for 4 billion years. You are warm because a star 93 million miles away warms the surface of a planet that gravity holds together. There is nothing to do with all of this except feel it. Feel the weight of your body. Feel the softness of whatever holds you. Feel the breath moving in and out. Gravity pulling your chest down with each exhale. Your lungs filling again as easily as a valley fills with morning mist. In and out. Down and in. The rhythm of a body at rest in a gravity well, the simplest and most natural thing in the world. Outside somewhere, rain may be falling, gravity returning water to the ground, or wind may be moving through trees, air flowing from high pressure to low, gravity shaping the atmosphere, or the night may simply be still, the air barely moving, the stars overhead completing their slow arcs, the moon, wherever it is tonight, shining down on a world that is mostly dark and mostly quiet and mostly asleep. And you can be part of that now, that quiet, that stillness, that sense of a world at rest. You've been held all your life by this gentle, invisible, patient force. It has never let you go. It will not let you go tonight. Whatever the morning brings, whatever the world holds, tonight you are here in your curve in space-time, And the universe is holding you the way it holds everything, completely, quietly, without any need for you to do anything at all. If you've been with us all the way through this story, thank you so much. A like or a kind comment would mean the world, and the playlist is always there for the nights when you need company on the way to sleep. There are stories about forests and oceans and birds and stars, each one made for exactly this, the quiet time between waking and dreaming, when the mind opens and the body settles and you are ready to rest. Close your eyes now if they aren't already. Let the last of the day's thoughts drift away like leaves on slow water. You don't need to hold on to anything. Gravity will do the holding. It always has. The world is quiet. The stars are where they've always been. And you are held. Good night.